In this lesson, we'll be looking at exponential functions. To begin with, let's recall the laws of exponents. When you have a to the s times a to the t, we can add powers. So this becomes a to the s plus t. Don't confuse that with a to the s raised to the t power. When you have power to a power, we multiply the exponents. So this would become a to the s times t. In this example, we're going to simplify this to a to the t, b to the t. 1 raised to the t power is simply just 1. A to the negative t, typically when we have negative exponents, we want to eliminate the negative exponents. So to do that, we're going to take it to the opposite side of the division bar. Think of it as a over 1 to begin with, and to remove the negative power, we'll simply put that exponential expression in the denominator, and it's now a positive t. And then a to the 0 is 1. The definition of exponential functions. It's going to look like this, where you have f of x equals a constant times a to the x power. Notice where the variable x is. It's in the exponent. That's what's making this an exponential equation or exponential function. C and a are just real numbers. A has the condition that it has to be positive, and a cannot be 1. C is not 0. C is what we'll call the initial value. A we'll refer to as the growth factor. So with that in mind, let's look at these. Is a an example of an exponential function? It is. The initial value is 3, and then the base of this exponential is 2. The base we also call the growth factor. In B, is B an exponential function? It is not. That's something we've seen before. This is just a polynomial. Look at where your variable is. The variable is not in the exponent. X is beside the 2. That's just a polynomial function. In this example, look at where your x is. The variable x is in the exponent. That means this is an exponential equation. And the growth factor is 4, also known as the base. Growth factor is 4. The initial value c is 1/2. Next, we'll look at graphing some simple exponential equations. Y equals 2 to the x. So we're going to choose some initial x values, say -3 to +3, and we'll see what the exponential equation does to those x values. So here we have 2 to the -3. Remember, the -3 power pushes that 2 to the denominator, so we can think of this as 1 over 2 cubed, which is 1/8. And then we would have 2 to the -2. That is 1 over 4. 2 to the -1, that's 1 over 2. 2 to the 0 is 1. 2 to the 1 is just 2. 2 squared is 4. And 2 cubed is 8. So let's plot those points on our graph here. -3, 1/8. We find -3 and go just a little bit above the x-axis. -2, 1/4. It's a little bit further up. -1, 1/2. 0, 1. 1, 2. 2, 4. And 3, 8. Connect the dots. Notice that it will not cross the x-axis on the left side. It looks like it might, but it's not going to. There's an asymptote here. We'll talk more about asymptotes a little bit later in future chapters, but essentially this curve is approaching the x-axis, but it's never actually going to touch it. It'll get closer and closer, but never actually touch it. So with an exponential equation like this, it's going to start kind of slow, but then it increases very quickly. Think exponential growth as population growth. Population is typically exponential. It starts slow and small, but then it increases very quickly. In this example, notice the base is 1/2. So it's going to be a very similar process, just the base has changed. So again, we'll start with -3 to +3. X is our independent variable, so we can make it whatever we want it to be. And from here, we will just do some plugging in. We have 1/2 to the -3 power. Remember that -3 simply flips the fraction. It pushes it to the opposite side of the division bar, which will flip our fraction. So we get 2 cubed is 8. Then we have 1/2 to the -2 power. That's the same thing as 2 squared, which is 4. And then 1/2 to the -1 power is simply 2. 1/2 to the 0 power is going to be 1. 1/2 to the 1 power is 1/2. 1/2 squared is a 4th. And 1/2 cubed would be 1/8. Very similar to the pattern we saw in the previous example, just backwards. So let's plot these points. We have -3, 8. -2, 4. -1, 2. 0, 1. 1/2, 2 1/4, and 3 1/8. And we'll plot a smooth curve. Again, we're not going to cross the x-axis. It's going to get close to it, but not actually cross it. And here's our graph of our exponential. Notice in the beginning it's decreasing quickly, but then it slows down. So we have a decreasing graph when our base is 1/2. Basically, think of a fraction between 0 and 1. And if your base is a whole number bigger than 1, then we're looking at an increasing graph. If you're ever unsure, just graph in the calculator. Next, we're going to look at some characteristics of exponential functions. And this first example is just looking at a generic a to the x, where a is bigger than 1. So think about the first graph we just looked at in answering these questions. The domain of that first graph was all real numbers. The range of that first graph is 0 to infinity. Again, if you're unsure, just refer back to the first graph we looked at. There are 0 x-intercepts. Remember, the graph never crosses the x-axis. And then the y-intercept is 1. Or if you want to write it as a coordinate, 0, 1. The horizontal asymptote of this equation is y equals 0. Essentially, it's the x-axis. Again, we'll focus on asymptotes a little bit later in chapter 5, but the asymptote is essentially the line that graph cannot cross. And the graph approaches the x-axis, or y equals 0, but it never actually touches it or crosses it. And in example, or question number 5, it says, will it be increasing, decreasing, or constant? In this case, we have an increasing graph. Again, just refer back to the first graph we looked at. It's increasing. Number 6, we have some special points that will always be on this generic graph of a to the x. Those are 0, 1, 1a, and -1, 1 over a. Don't worry about memorizing those. These are just some facts that occur for any exponential. And then also note that the function is 1 to 1. Referring back to that first graph, it passes the horizontal line test, therefore it is 1 to 1. In this next example, we're still looking at f of x equals a to the x, just a generic graph, but this time our base is between 0 and 1. It's a fraction. So when we're answering these questions, think about the second graph we looked at. The domain, all real numbers. The range, 0 to infinity. Still no x-intercepts, and the y-intercept, 0, 1. The horizontal asymptote is still y equals 0, the x-axis. And if we refer back to that second graph, we saw that it was a decreasing graph. Some special points that will always be on that generic a to the x. -1, 1 over a, 0, 1, and 1a. Notice these are slightly different than the previous graph. Don't worry about memorizing those. Also note that the graph is 1 to 1. It passes the horizontal line test. So all of these characteristics and the characteristics from the previous example, don't worry about memorizing these necessarily. You can always just look at a graph and determine this information if you need it later. These are not things you necessarily need to have memorized. Let's look at solving exponential equations. Today we're going to look at a shortcut that only works for very specific types of equations, and you have to recognize when it works and when it doesn't. We'll focus on examples that look like a to the u equals a to the v. Essentially, you're going to isolate both exponential expressions on the left and the right, and we're looking to see if they have the same base. If they do have the same base, we can essentially ignore the base and set just the exponents equal to each other. Now for today, this trick is going to work, but in the future, this will not always work. It doesn't work for every single exponential equation, but if you can force this to happen, it will work. You have to be able to force the left side and the right side to have the same base and nothing else. If we can do that, this little trick is going to work. So looking at this example, we have 5 to the negative x equals 125. On the left, we have a relatively simple exponential expression. So we want to ask ourselves, can we rewrite the right side so that it has the same base raised to a power? And we can. Think of the left as 5 to the negative x, and we want to be able to write 5 to a power so that we get 125. And we can do that. 5 cubed is 125. And if we can do that, notice we have 5 to a power equals 5 to a power. There's nothing else around those 5s. It's just 5 raised to a power equals 5 to another power. If that's the case, we can simply drop the base and set the powers equal. Negative x equals 3. And then, finally we divide, and x is equal to negative 3. So I'll prove this a little bit later. Right now we don't have the tools for me to prove why this works. So for now, just trust me that we can do this trick. Later on, we'll get some extra tools and learn more about exponentials and logs, and I'll prove to you that this trick actually does work. For now, just trust me. Next, we have a slightly more complicated example. Notice that all three bases are different, but we want to be able to write them as a power of the same base. So it looks like the right side is pretty simple, right? We have 3 to the negative 1 power. Let's see if we can rewrite the others as 3 to a power. And it looks like we can. 9 we can write as 3 squared. So we have 3 squared raised to the 2x. times 27 we can rewrite as 3 cubed raised to the x squared equals 3 to the negative 1. Now we need to go through and simplify using our exponent rules. The first thing we can do is take care of this. This is a power raised to a power. So when we have a power raised to a power, we multiply. This becomes 3 raised to the 4x times, again, we have power to a power, so we can multiply these two powers, those two exponents. We get 3 to the 3x squared, and that's equal to 3 to the negative 1. And now we have a base times a base. You have 3 to a power times 3 to a power. When you have bases that are being multiplied, we can combine them into a single base and we add the exponents. And I'm going to reorder it so that it looks a little neater. We're just adding those powers. Next, notice we have 3 to a power equals 3 to a power. We have both sides written as a power of the same base. If that's the case, we can simply drop the base and set the powers equal. 3x squared plus 4x equals negative 1. And now notice you have a quadratic. So quadratics we set equal to 0. 3x squared plus 4x plus 1 equals 0. At this point, you can choose whatever method you prefer. You can try factoring using the AC method. You can try the quadratic formula. It doesn't matter. I'm going to try the AC method to see if it works. A times C is 3. We need two numbers that multiply to 3 and add to 4. That will be 3 and 1. So we have 3x squared plus 3x plus x plus 1 equals 0. Factor by grouping. Notice the parentheses are the same. That's a good indication that we're on the right track. Continue factoring. Set each factor equal to 0. And we get x equals negative 1 and x equals negative 1/3. And we've got our solutions. In the next example, we have a bunch of e's. Don't let those e's throw you. E is just a number, kind of like pi, right? Pi is a number that we use a lot in the math world. E is another number that just comes up naturally often in math and really in nature. You don't have to worry about its value. Just know that E is a number similar to pi. So it looks like on the left side we have e raised to a power. We can't really simplify the left side. The right side we can do a little bit of work with. So let's see if we can rewrite using our exponent rules. I'm going to start by copying the e to the 3x and rewrite this piece with a negative power. We'll pull that e to the numerator, and when we do that, remember, it changes the sign of your exponent. So now that our e is on the same level as our other exponential expression, now we have e to the 3x times e to the negative 2x. If we're combining these, we add those powers. So we have e to the 3x minus 2, or plus negative 2. We combine them using the addition rule. Notice now you have on the left e to a power and on the right e to a power. If this is the case, when you have both sides written as a power of the same base, we can simply eliminate the base and set the exponents equal. X squared equals 3x minus 2. From here, it's a quadratic. Set it equal to 0. X squared minus 3x plus 2 equals 0. And you can choose any method you want. It does not matter how you solve from here. It looks like factoring will work, so let's use factoring. It's fairly quick and easy. Two numbers that multiply to 2 and add to -3 are -2 and -1. Set each factor equal to 0. And we get 2 and 1. In this application, the normal healing of wounds can be modeled by an exponential function. If a sub 0 represents the original area of the wound and a equals the area of the wound, then the function a of n equals a sub 0 e to the -3.5 pi, n, describes the area of the wound after n days, following an injury when no infection is present to slow the healing. Suppose that a wound initially had an area of 100 millimeters. Part A. If healing is taking place, how large will the area of the wound be after 3 days? A of n, we're going to replace the n with 3 days. A sub 0 is our initial amount. They tell us the initial area is 100 square millimeters. So I'll plug in 100. E to the -0.35, and we're replacing n with the 3 days. From here, we'll just throw it into the calculator. So 100. E is actually located in two places. Notice it's in blue above the divide, or it's in blue above the natural log. I'm going to use the one on the left because it automatically gives you an exponent. So second natural log will give you the e to the power, and we want this to be -0.35 times 3. Enter, and it looks like the area of that wound is roughly 34.99. And the units here are square millimeters. The next question is, how large will it be after 10 days? So the area evaluated at 10 days. The initial value is still 100. E to the -0.35 times 10 days. So we're just going to plug this into the calculator. A shortcut to get the previous command is second enter. That'll just pull up the previous command. All we need to do is edit the 3 and make it a 10. So now the area has shrunk considerably. The area is roughly 3.02 square millimeters.